Hello everyone and welcome to part 2 of the 3.5 notes where we're going to be talking about rational functions. In particular, we just studied the infinite kind of behavior that can happen around asymptotes on a rational function. We want to talk about first because this one's a little bit easier to get a handle on, and it's something similar to what we've seen before. We want to talk about the vertical asymptotes for a rational function. And of course the vertical asymptotes, those end up being the places that we've seen before where a function might not have a certain element in the domain. You know, we've seen before where you might have a function like f of x equals maybe x over x minus 1, and we're wondering what is the domain for this function. Well, the domain, it would be everything except for 1, right? Because 1 will cause us to divide by 0. So it would go basically negative infinity up until 1, and then it will go 1 up to infinity. And the reason why 1 is not in the domain over here is because this function actually has a vertical asymptote at 1. And so the way that we find the vertical asymptotes, it's very similar to the way that we would want to evaluate the domain for this one, except for there's a small difference, and that's what we'll talk about. In general though, the vertical asymptote, we actually can give it a definition, that the vertical asymptote is any x value where we have that kind of infinite behavior that we saw before. So if the y values of the function either approach positive or negative infinity as the x values approach that number, then we call it a vertical asymptote. So basically, if we have, for example, this picture, it's supposed to say as x approaches c from the right, f of x is going towards infinity, so we'd be expecting a rational function that's coming in this kind of a shape where it's going up towards infinity as you come to the right. And then it doesn't have to be the case, but a lot of times it will alternate where now if you come from the left, it will go to minus infinity. It is possible to have them both going the same way. We could have a kind of a situation like this. And it's possible to have them flipped as well, where maybe here we want to say as x approaches c from the right, f of x goes to negative infinity, so it's coming down this way. And then this could have the case where maybe from the left, it could be going up. These kinds of shapes are all possible around a vertical asymptote. For example, x approaches c from the left, f is going to negative infinity, so it should be coming down like this. But it's possible for it to be the same on both sides as well. And so any of these kinds of shapes are possible around a vertical asymptote, but what's important is just the fact that the y values are going towards infinity as the x value is approaching the c there. Now, whether there's a vertical asymptote or not, it has to do with whether it's possible to cancel a factor from the top and bottom, from this p and q. If they have a common factor that's cancelable, then it can cause there not to be a vertical asymptote there. And so what I mean by that, and we'll see an example of that here, is that if you have a function, say it's a function like p of x over q of x, where these are both polynomials, so this is a rational function, it might be possible to factor out something from p of x. Say we're able to factor out this thing like x minus c. And then there's just going to be something left over. I will call it maybe p star of x, because we already factored out something, so it's not really p of x anymore. We get whatever we get by doing this, you know, synthetic division or long division or however you want to achieve this factoring. And then maybe we're able to factor the same thing, x minus c. It might be a factor of q of x as well, so we'd get kind of a q star of x kind of situation going on bottom. Well, now that we can cancel these two factors, then x equals c is not going to be a vertical asymptote. And that also, I should make a little bit of a disclaimer, because maybe x minus c, it might be still a factor of q star again, because you know factors can happen more than once. Here we're assuming that it doesn't happen more than once. This is the only factor of x minus c that we can take out of the top and bottom to cancel. And so we would get the conclusion from this one that x equals c is not a vertical asymptote. Actually, it would end up having a different behavior. It still is not in the domain. You know, c is still not possible to plug into the original, so c is still excluded from the domain. But the nature of that one, we would have that this point, the point whenever you plug in c, which it would have the value c, and then f of c would be the y value there, that actually would end up just being a hole in the graph. So we'll see some examples for doing that one as well a little bit later on, but just wanted to introduce that idea to you now. But anyways, we would like to identify the vertical asymptotes for some of these problems. So let's just see an example here. We have for this one a rational function, of course, because there's a polynomial on top, there's a polynomial on bottom. Now we should ask ourselves, is it possible to factor the bottom, because we want to find out which x values will make the bottom be 0. And those will be a vertical asymptote, those x values that make the denominator of this function be 0. Those will be vertical asymptotes unless we can cancel with this x minus 3 in the top. So we should go ahead and factor the bottom. Here it factors as, we've got minus 5, so we need things to multiply and give negative 5, and they should add up to negative 4, so it will go x minus 5 and x plus 1. These will be the factors. They are not x minus 3, so we're not able to cancel anything. So the vertical asymptotes for this one will be x equals 5 and also x equals negative 1. There will be 2 vertical asymptotes for this function. Now let's see for this one that goes x minus 3 on top again, but now we have a different denominator. So x minus 3 on top, and we can factor the denominator here. We need things that will multiply and give negative 3 and add up to negative 2. So it will go, one of the factors will go minus 3, the other factor will go plus 1. And notice here we have x minus 3 on top and bottom, so we can cancel this one. Always, if you cancel the whole side of a fraction, it's a good idea to replace it with 1 there. And so this actually becomes the function 1 over x plus 1. And so x equals 3, this will not be a vertical asymptote. It actually, there would be a hole there whenever x is 3 and at the associated y value. So the only vertical asymptote is actually the value that will make x plus 1 be equal to 0. So of course we can subtract 1 from both sides. If the x equals negative 1, this is the vertical asymptote. It's a vertical asymptote. It's also, let me write, it's the vertical asymptote for this problem. And then when we take a look at number 4, we're wondering, is there an x value that will make the denominator be 0? If so, there will be a vertical asymptote there, but of course x squared plus 25 equals 0. This thing has no real solutions because it would go like x squared equals negative 25. And then you might be asking yourself, how are you going to square a number and get a negative answer? It's only possible if you plug in a number that has I in there. But our graphs, every type of point on this graph is a real number. So if there's no real solutions, then we would say there is no vertical asymptote for this one. And so that does it for our discussion of vertical asymptotes. We're going to come in here talking about horizontal asymptotes, and then there's another kind that's called a slant asymptote. We'll see that one in future videos. And so thank you guys for watching this one, and I'll catch you in the next one.